In machine learning, we have this dream of working with perfect, clean data that just behaves. But let's be real, the real world is messy. It's full of weird outliers and exceptions. So the big question is, how do our models actually deal with that? Let's dive into this huge dilemma. Do we build for a perfect world or one that can actually survive in the practical, messy one?
And really, this is the million-dollar question, isn't it? What happens when your data points aren't just neatly sorted into two perfect little groups? What if there are a few troublemakers that just refuse to play by the rules? Does your entire model just fall apart? Or is there a smarter, more flexible way to handle the chaos?
So on this slide, you can really see these two completely different philosophies in action. Over on the left, you've got the hard margin approach. This guy is a total perfectionist. It will bend over backwards, creating this super complex, wiggly line just to make sure every single point is classified correctly. The problem? It's way too sensitive. It freaks out over every outlier, and while it might be perfect on the data it trained on, it does a terrible job with new data. That's a classic case of what we call overfitting. But on the right, you've got the soft margin approach. This one's way more chill. It goes for a simpler, cleaner boundary and is totally okay with getting a few points wrong. It sacrifices a little bit of that perfection to be way more reliable in the real world.
Okay, so let's dig in a little deeper. Why exactly does that super strict, perfectionist approach fail the second the data gets even a little bit messy?
A hard margin support vector machine, or SVM, is designed to do one thing really well: draw a line separating two groups of data with the widest possible street, or margin, between them. And the key rule is absolutely no points are allowed inside that street. But what happens if the data isn't perfect? What if there's just one single data point on the wrong side of the line? Well, the model just breaks. It literally can't be built. Its greatest strength, that absolute, uncompromising strictness, is also its biggest downfall. It just can't hang when there's any real-world noise.
So how do we fix this? Simple. We introduce a little bit of flexibility. So let's talk about the soft margin SVM. It's a really clever and pragmatic solution that knows when it's okay to bend the rules a little. And the logic here is actually beautiful in its simplicity. First, the main goal is still the same. We want to find that nice, wide, stable margin. That's what makes SVM so powerful in the first place. Second, we make a trade-off. We consciously decide to let some points be misclassified. And third, and this is the magic part, we control this whole trade-off using a special setting called a hyperparameter. It's called C, and you can think of it as a knob that sets the cost or the penalty for each mistake.
So this C parameter really is just like a dial you can turn. If you crank C way up, you're telling the model, hey, mistakes are super expensive. Avoid them at all costs. And so it starts acting a lot more like that strict, hard margin perfectionist. But if you turn C way down, you're basically saying, look, a few mistakes are no big deal. Just focus on getting a nice, wide, stable margin. This lets the model ignore the outliers and generalize better, which just means it'll perform way better on new data it's never seen before. It's all about finding that perfect balance.
All right, so that's one way to handle messy data. But what if we threw out the whole idea of drawing lines altogether? What if, instead, our model made decisions just by asking a series of simple questions? Well, this is the entire idea behind another incredibly powerful tool: decision trees.
Seriously, just think about a game of 20 questions. You don't try to guess the answer in one single brilliant move. No, you start with a really broad question, right? And based on the answer, you ask a more specific one, and then an even more specific one, until you finally zero in on the answer. Well, decision trees work in exactly the same way. It's basically a flow chart of questions, all designed to sort and classify data.
And here's the basic layout of one of these things. Right at the top, you have the root node. This is the single most powerful question you can ask to start splitting up your data. The different answers to that question send you down different branches, which lead to internal nodes, which are just more questions. You just follow the path down until you hit a leaf node, and boom, that's your final answer, your prediction. It's so intuitive, you can just look at it and see exactly what it's thinking.
But this all leads to one really important question, right? How does the tree know which questions to ask, and in what order? I mean, how does it find the best question to ask at each step? Well, the secret sauce lies in two key concepts: entropy and information gain.
First up, entropy. Now it sounds a little intimidating, but it's really just a measure of chaos, or how mixed up your data is. Imagine you have two jars of marbles. One jar is filled with only red marbles. That's a super pure set. It has zero entropy, because there's zero uncertainty about what you'll pick. Now imagine the other jar is a perfect 50-50 mix of red and blue marbles. That is maximum entropy, total chaos. The whole goal of a decision tree is to ask questions that bring that chaos, that entropy, down.
And that brings us to information gain. This is basically the reward the tree gets for asking a good question. It's a number that tells you exactly how much the entropy, the chaos, goes down after you split your data based on that question. So at every single step, the tree looks at all the questions it could possibly ask, calculates the information gain for each one, and it always picks the one that gives it the biggest aha moment, the one that cleans up the most mess.
So, for instance, in a classic dataset people use to predict whether or not to play tennis, the tree needs to pick its very first question, that root node. It runs the numbers and calculates the information gain for asking about the outlook, the humidity, and the wind. And as you can see from the chart, asking about the outlook, is it sunny, overcast, or raining, gives the highest information gain by far. It does the best job of separating the yes, let's play, from the no, let's not. So that's exactly where the tree starts.
So we've just looked at two completely different ways of thinking about how to solve classification problems. Let's put them side by side for a final comparison to really see what makes them tick.
So on one side you have the soft margin SVM. It's all about geometry. Its mission is to find the single best line or curve to separate the data. And its core idea is to make the street between the data as wide as possible, even if it means a few errors. The results are powerful, for sure, but they can also be really hard to understand. It often feels like a black box. But then you have the decision tree. It's all about logic. It asks a series of simple questions, chopping up the data into neat little rectangles. Its core idea is just to get the most information possible out of each question. And its killer feature? It's incredibly easy to interpret. You can literally just look at the flowchart and follow the logic.
As the creator of our source material put it, and you can see his original quote here, once you really get these core ideas, it all becomes pretty straightforward. The quote translates to, "This is very easy, free marks." And that's the point. Understanding these different approaches isn't just about passing a test. It's knowledge that really empowers you to build smarter, more practical models. So I want to leave you with a final question to chew on. When you have to make a complex decision in your own life, which approach do you think you naturally use? Are you more of a flexible line drawer, trying to find one perfect rule that works for most situations, kind of like an SVM? Or are you more of a systematic question asker, following a step-by-step flowchart in your head, like a decision tree? There's no right answer, of course, but it's pretty fascinating to see how these big ideas in machine learning actually mirror the ways we think every single day.